regional internet registry as we recognize today. APNIC was the second one, and then we have the other RIRs coming in after that. So all of this combined really to try and put a bit of brakes on the IPv4 address consumption. So organizations tended to get the address space that they needed rather than the address space that they actually wanted. And there was quite a bit of difference in that. And I still remember, even in the late 90s, I still seeing organizations, especially in Asia where I'm working, of saying, well, we're a very big organization. We should be getting, okay, rather than trying to do any proper justification as to what they actually needed. The thing is with v4, the 32-bit address space, that gives you 4 billion hosts, theoretically. But there's this thing, the HD ratio described in RFC 3194, which realistically tries to describe, well, realistically, how many hosts you can get on or within a 32-bit address space. So realistically, it's probably more like 250 million hosts, which, if you think about it, is not really a lot. World population is over 6 billion. 250 million hosts is not really a great deal. So then we had the boom years. So this is probably, 96 through to 2001, before the dot-com bust. So IPv6 development, notice development, was in full swing, because all the v6 folks were excited, all these things we're going to do and add and so on and so forth. There was a huge amount of v4 consumption. The registries were handing out address space at high speed. Many of the v6 specifications were being sorted out, and there was a huge number of different transition mechanisms were being developed. Because in that type of thing, at that time, people were thinking, right, we're going to be going to v6 round about 2000, 2001 or so. Various people were predicting running out in 2004, 2005, and others weren't. So there was a huge amount of mechanisms being developed to try and encourage people and show people how easy it was to just move over to v6. There was a 6-bone, which was the experimental v6 backbone sitting on top of the internet. That disappeared or was shut down in June 2006. But in its heyday, there were participants from over 100 countries involved in that. And the 6-bone literally was a tunneled internet infrastructure on top of the real v4 internet. And there were many early adopters, so Japan, Germany, France, UK, many of these countries were jumping in and giving big incentives to use v6 and so forth. Then we had the bust years after the dot-com crash. Well, some people call it, well, that's when the internet became boring as far as investors were concerned. It was no longer the big new wonder technology. It was pretty much what everybody used. And a lot of people lost a lot of money, business, lost their jobs and so forth. But the internet still was there. It became mainstream, and it's just what we used. Along with that, the v4 consumption slowed. If you look at the registry stats, you find that the amount of allocations they were making in this period reduced quite significantly. They were still getting new members, but they were losing a lot of old members as well. So things cooled off. And there's a lot of indifference as well. The early adopters of v6 just surged on forwards. Yep, v6 is going to happen tomorrow. And, well, the skeptics became more skeptical because, quite literally, they'd seen all the IPv6 talk from 94, 95, and they were sitting in 2001, 2002, and still nothing had happened. Still things weren't working properly. And so you got this fairly significant division of really skeptical people and really enthusiastic people. And the rest of us sitting in the middle were like, yeah, well, whatever. And so the reaction was you saw even more transition mechanisms being developed. And that probably wasn't too useful in the longer run. From 2004 to today, well, we've got resurgence in demand for v4 addresses. There's 19.5% of the address space still unallocated. At the rate it's being handed out by the registries, we're going to run out sometime August, September, October 2010. I think all the predictions have converged somewhere around about that time. At least that's when the IANA pool will run out. Whereas the registry pool will probably be early 2011. So the various other issues surrounding with that. I'm not going to go into the whole address policy discussion and so forth, but if you join any of the registry policy mailing lists, you see there's a huge amount of discussion about how we're going to run out of v4 addresses and what's going to happen after that and so on. So if you've got lots of spare time, have a look. If you're interested in how this is going, you should have a look as well. But I would say, especially from technology strategy within your company, I mean, one question I ask many CTOs in my travels is, what are you going to do? What's your business plan after August 2010? And they always say, well, what do you mean? What do you mean? Well, you can't go to Aaron to get more v4 address space. What are you going to do? And nobody's thought about that yet. I mean, I'm not saying, oh, you should be running off doing v6. It's more a case of what do you need to do? People have talked about the market for address space. I mean, I suppose there already is a market for addresses, which is probably fine in an affluent society. But if you look around the world, how much of it is affluent? You look at some countries where, well, the monthly income is probably $100 for a person, right? Compare that, I mean, how are these people going to spend $1 million to get a /24? They can't. So it kind of excludes those from getting real v4 addresses, and so they have to use something else. Now, the main thing with v6 is it offers huge address space. Right? So the v6, that's the main motivation today that's left, is v6 offers huge address space, and that's kind of what I'm going to walk through next. So current perception really is that v6 hasn't taken hold yet, which is, well, it's true. I mean, not many of us are using v6. The v4 address runout is not headline news. I mean, you don't switch on CNN or BBC World and see, it's like not the top news story. It doesn't even feature in there. It doesn't even feature in the tech section of any of these media. But it's at least started to make some kind of impact in the registry policy thing. And, you know, we've talked about it enough at NANOG over the few years. I suppose at least we're aware of it. But yes, there are plenty of discussions and run-out plans and so forth all being proposed within the registry system. And, you know, they're all weird and wonderful. And those of us from the operations community who also play in the registry policy arena, I suppose, well, it's not so much frustration as, well, we have to sit there and try and explain to a lot of the policy folks why some of the suggestions about run-out don't really make a great deal of sense. Private sector, of course, needs a business case to do anything. I mean, you can't just sort of walk into a company and say, right, we're going to switch over to v6 and, well, it's going to be wonderful. They need a business case to do anything. I mean, I work for a vendor. Vendor needs a business case to do anything. They don't just do stuff because, hey, somebody said so. And of course, any private sector business is going to say, right, what's my return on investment? And at the moment, it's like, well, you get bigger address space, and there's no obvious return of investment in there. So the reality is something has to be done. If we want the internet to grow, as it has been growing really beyond 2010, we need to do something. So whether it's some super-duper amazing net for IPv4, or using IPv6, or doing something completely different that we haven't even thought about. But something does need to be done, and people need to focus on that. Just some more numbers to look at. I mean, internet population, 630 million users at the end of 2002. It's doubled by the end of last year, and that's 20% of the world population now. And we're looking at places like South Asia, especially India and China, becoming more and more internet literate and so forth, and really piling onto the internet at high speed. So where's it going to be in 2-3 years' time? If we jump forward to the end of 2010, how many internet users are there going to be? How are they going to connect? I mean, the US was one of the early countries to be part of the internet, so I've got a lot of the early address space. So if you look at the averages, almost 4 IPv4 addresses per person. We repeat this the world over, 6 billion population, 23.4 billion v4 addresses. Well, there aren't that many. So if we want to do the same kind of density, how are we going to achieve that? China today uses 5.5/8s. Okay, and that's a pretty significant amount, especially if you start looking at some other economies around the world. RFC 1918 is only so big, and we already see several organizations saying, well, look, you know, we've used up the entire RFC 1918 space. What do we do next? I mean, Alain Durand from Comcast did a presentation, NANOG 37, explaining what the particular issues were there. And I can repeat this from many other providers around the world who face the same issues. They've used up the entire private address space for managing just for management within their own network. So what do they do next? Because having overlapping private address space doesn't scale or doesn't work for them. The policy development process of the registries turned down a request to increase private address space. That was a couple of years ago, although interesting enough, a policy proposal has been put up at APNIC meeting, which is next week, to try the whole thing yet again. And so people don't realize what's happened in the past, so we're going to try and do it again. And where's this address space going to come from? Well, the existing v4 pool, which means that there's then less usable v4 pool for everybody else. 240/4 has been proposed as a new private address space. But then the issue is, how do you backfit it to all the IP systems that are out there in the world already? I mean, routers can forward these packets, but can they actually set up interfaces with them? Can you configure it on your Windows PC? You can't. So from operations and operating system support, application support, I mean, pretty much everything is there to some extent. I'm not claiming that everything's complete, but at least to some extent you see that, the macOS and my Apple here, BSD, Linuxes, the various commercial operating systems, they all have IPv6 support to some extent. Not saying it's perfect, but at least it's there to some extent. Applications, more and more applications seem to be becoming, protocol agnostic. I mean, we saw in the V6R, pretty much you can start up your web browser, and it will use either v4 or v6 transport, whatever's there. But we certainly should not be trying to expect the end user. And could you explain to your mother or your father that, okay, if you want to use the v6 internet, you've got to click on this button, and the v4 internet, you've got to click on that button. You couldn't do that to somebody. They just want to switch it on, and they want to get their email and browse the web. They don't want to have to figure out which protocol they're going to choose. So there are quite a few websites that are tracking what the state of the different applications are. And I mean, I've put one up there that seems to have a list a fair number and what's happening with them. If you look in the ISPs as well, there's several different market segments. The internet exchanges, the regular carriers, you've got the regional ISPs, wireless providers, and so forth. ISPs have to go to the registry to get the v6 prefixes. So the URL I've put up there it's one example of what the registries do. Each registry has their own v6 allocation policy. Large carriers tend to do things depending on what the customers ask for. So some of them are running trial networks, and others are running full commercial services. I mean, some may be full services, but they don't tell the customers about it. Others are proper full services that you can pay real money for. Regional ISPs tend to focus on the specific markets. So again, if their particular market doesn't demand v6, then they don't do anything about it. There's been a lot of discussion by operators and so on about transition. So when I've put up the URL there that the cluster 5 one that we talked about in the V6 earlier today, and one of the many presentations looking at some of the operational reality. And more people who focus on some of these things, hopefully, the more time we can spend looking at how V6 could be deployed. Then the endless question, of course, why not just use NAT? The many service providers who are quite experienced at using single, double, even triple NAT. There are issues with that as well. I mean, the obvious one of breaking the end-to-end model, which is very important to some people. Layering of NAT devices causes problems. How do you scale NAT performance for a huge network? Because a NAT has to basically remember the state for every single connection running through it. So how do you build a super-duper massive NAT box? So it makes it kind of hard to try and offer proper services simply sitting behind NATs. And I've listed some of the things here. I'm sure there are loads of other implications as well. I mean, there's a network security issue that worries people. I mean, how do you properly do IPsec and so forth through NAT devices? When an application isn't NAT friendly, you've got to go and upgrade your NATs. That can be problematic as well. I certainly remember issues with that in the earlier years of, say, new applications like SIP and so forth, or protocols like SIP, having to upgrade NATs just to be SIP friendly. Application layer gateways, what about doing mergers and so forth? Mergers between different organizations using the same NATed address space. How do you join these networks together? Maybe you can double NAT and have something else sitting in between. How do you do multi-homing? I mean, I've seen NAT being used to help with multi-homing or as an alternative to using BGP, but doing this on a huge scale, nobody's really looked at any of that. So there's a big worry about some of the scalability. And there was an old RFC, I mean, it's been around for a few years now, RFC 2993, that looks at some of the architectural implications of using NAT. So I don't know, my personal feeling is that there is a need for a larger address space. The solution that we've got, the only solution we've got at the moment is really to use V6 to do that. I mean, we could try and use that to do NAT to do this. NAT is going to be around for a long time. The many parts of the world, if you look at, say, parts of South Asia and Africa, they're already very, very experienced at using NAT devices and layered NAT devices within their own networks. So NAT is going to be with us with a while. Some ISPs are going to choose to use NAT rather than go down the V6 road. And of course, there's going to be the market for V4 addresses. Like it or not, I have a real big feeling that this is what's going to be coming towards us. And there are a lot of challenges ahead, of course. So we'll look at the protocols and standards now, really to what has changed. A lot of people say, oh, well, the address space in V6 has increased over V4 by 4 times. It hasn't. It's the length of the address has increased by 4 times. Okay, the length has increased by 4 times from 4 bytes to 16 bytes. So it's many, many, many orders of magnitudes bigger than the existing V4 address space. The header format has been simplified, and I think this mostly came from the equipment vendors. So the header is now fixed length rather than being variable length. Checksuming's been removed from the IP network layer. There's no hop-by-hop segmentation anymore. We've got to use PathMTU discovery. So those folks who love filtering all ICMP out of the network will probably have to rethink that particular issue. 64 bits alignment was exciting in 1996 and 97 because 64-bit processors were new and amazing things. But nowadays, 64 bits are like, yeah, well, everything's 64-bit processor, so it's not so much of a thing. Authentication and privacy capabilities, I mean, that was one of the big things for V6 early on, in that IPsec is mandated. But of course, IPv4 has caught up with a lot of this now, so how much of a big win that is no longer clear. And of course, there's no more broadcast in V6 either. That was one of the bigger things with V4 early on. And I've put up a graphic here that just tries to show what's changed, what's stayed the same, and what's new. So everything in, okay, it's appeared the right color. Everything in orange basically has stayed more or less the same. So the source address, destination address is the same, the version number, the same field in the header. Obviously, the version number is different, but it's the same field. A lot of the V4 fields have now disappeared, like the IP header length, identification, various flags, fragment offset, because you don't get those now. Header checksum's all gone. Various options, they've all gone. And of course, there's no need for padding anymore. What's new in V6 is this flow label. Talk about that in a little bit. And otherwise, some of the fields have basically had their name changed and the position changed, but they do roughly the same thing. So traffic class is the new name for a type of servers. Payload length is the new version of the total length. Time to live and protocol are really replaced by hop limit and the next header and so on. So things have been simplified, hopefully. And it probably helps the equipment manufacturers or the protocol manufacturers probably more than you and me sitting here trying to configure it on your network. So larger address space, so just over 4 billion possible devices for V4. For V6, well, 3.4 times 10 to the 38. I wrote the number out very, very big, but it's completely silly numbers if you look at it like this. 5 times 10 to the 28 addresses per person on the planet. I mean, it's just stupid numbers, but I put them up there just to show what the size really is. And you'll see later that the size is not really as amazing as you see, the way that the V6 space has then been chopped up for different categorizations, as I'll show you in a bit. How was the size chosen? I mean, this is probably oversimplifying it, But generally the impression was that some people want fixed length 64-bit addresses, because at the time 64-bit was vastly bigger than 32-bit. It'd be more than enough for anything and for anybody. And it would be efficient for software processing and so forth. Some people wanted variable length. So you had a variable length address size, so it could be 32-bit, but we started adding on pieces, it would all just be fine, possibly up to 160 bits. And that would be compatible with the OSI NSAP addressing plans. It would allow us to do auto-configuration with the IEEE 802 addresses. And so we could start with, say, something nice and short and then grow it. It's a bit like the phone numbering system. Once you run out of numbers in your current addressing plan, well, you just insert a digit somewhere and life goes on. But the result was, now, take a happy compromise, or well, I think compromise is probably the best word, happy compromise, 128-bit fixed length. Representation, well, this is the other new thing. Certainly for some people who are new to this, it's a bit of a surprise. Rather than the good old decimal dot notation we've been using for v4, it's hexadecimal colon notation for v6. So if you haven't done any hexadecimal in your life before, you probably should start go learning it. It's not too bad, really. I mean, it's just, apart from 0 to 9, you carry on A, B, C, D, E, F to represent 10 through 15. So think about it that way. It's probably not so bad. And the addresses end up being pretty huge. So you get typical addresses, something like this, filled out with zeros and so forth to try and fill up the space to the full 128 bits. Leading zeros between the colons, leading zeros can be dropped. So I can actually reduce this 203 and all these zeros down to 2031 colon 0 by itself. So that's handy. It helps to reduce the amount of typing folks have to do. Successive fields of 0 can be represented as a double colon. So you can just simply drop a 0 sitting there by itself. But you can only do it once. If you do it twice, then the router doesn't know, or the device doesn't know where the padding, the zeros padding needs to go in. So something like 2031 colon 0, this one is perfectly okay. But this one here, having two sets of double colons, this is not okay. Another other thing you can get is something like address, which is all zeros colon 1, can just be represented as double colon 1, which is the loopback address in v6. And unspecified address, all zeros, is basically a double colon. So from a typing point of view, you can get some kind of shortcut like that. But generally, we're dealing with larger colon-separated hexadecimal addressing. Folks used to use v4 compatible address, and it doesn't seem to be used anymore. I haven't found anything that says this shouldn't be used anymore, but everybody tells me it seems to be deprecated, and I haven't actually found the document that says that it is. But nobody seems to be using it. It's just the addressing was compatible. It didn't mean that you could use this address on a v6 host to speak to the v4 world. Some people thought that. It doesn't. It's purely an addressing that's compatible with v4, which is, well, I'm not quite sure what the intention really was there. The other thing that came up early on was, well, how do we type in v6 addresses for URLs? So I've just thrown this in here. You actually have to put the URL inside square brackets because, of course, colon is used to represent what the port number is for connecting to your website. So putting the v6 address inside brackets was the way of, I suppose, escaping the colons inside the addresses. So this is going to be pretty cumbersome for users, and I can't really imagine that too many people are going to try and do this. So it sort of means that the DNS really has to work for v6. I mean, we could get by with it in v4 because typing in a v4 address wasn't so bad. But a v6 address, especially the bigger, longer ones, the chances of mistyping or getting something wrong in that is fairly high. So using proper names is really going to have to be available for everybody. The actual prefix representation is unchanged. So for v4 address with something like 198.10.00/16, for v6, again, it's the v6 address / the mask. So it's exactly the same representation as in v4 CIDR. So at least that's familiar. They haven't gone into some completely different notation altogether. The v6 addressing rules are covered by multiple RFCs. I mean, RFC 4291 basically describes the architecture itself. So we've got 3 different address types. We've got the unicast address, which we're familiar with in v4. We've got anycast addresses, which is basically 1 to nearest. That all comes from the unicast address space. And we've got multicast, which is the 1 to many. So again, it's the similar address types as to what we have in v4. One difference in v4 is that a single interface can now be assigned multiple v6 addresses. We don't have the case in v4 where an interface can only have 1 address. Although again, since v6 was first started on, you can now have multiple v4 addresses on, say, Unix systems, on routers, and so forth. But in the early days of v4, that just wasn't really feasible. What else? There's no broadcast address anymore, so broadcast has been replaced by multicast. Certain addressing, so we've got unspecified address is all zeros. So let's just /128. Loopback address, rather than 127.0.0.1, it's now just /1/128. Global unicast address space, so far, all the assignments and allocations made by the registries are coming out of the 2000 /3 address block. So that's about 1/8 of the entire v6 address space is being used for existing allocations from the registries. We've got link local unicast addresses, something called unique local unicast, which again I'll talk about in a while, and of course the multicast address space is really the last /8 at the top of the range. So if we look at the v6 global unicast address space, you can already see that the massive number of 128 bits that we had has been chopped down quite substantially. The final 64 bits we've got basically are intended to be used for the host. Okay? And then the next 16 bits are for the site, so-called subnet ID, and then the first 48 bits are being used by the provider. So I'm going to go into these in a bit more detail in the next slide. But we've got this kind of hierarchy between provider, site, and the actual host/LAN. So what we had as 128 bits is actually fairly significantly reduced. This hierarchical structure was intended to simplify aggregation. As I say, intended to simplify aggregation. I think in real life, as we look at the v6 routing table today, that hasn't really happened. If we look at the actual allocation process, so as I was saying, 2000/3 is the global unicast block that's being used for allocations at the moment. Out of that, each regional internet registry gets a /12. Okay, so each RIR is getting a /12. Each registry will then assign a /32 out of this /12. So you as the ISP will come along to the registry and say, I need v6 address space. You will get a /32. Okay? And it pretty much works like that. You don't really have to jump through the major hoops that you have to do for v4. You can pretty much turn up and say, I'm going to deploy v6 on my network, give it to my customers, and the registries respond with a, here, have a /32. Okay? And that's what you get. I mean, it's not a case of, oh, well, you're a small ISP, maybe you should only get a /48 or something. It's not. You get a /32, end of story. If you can use more than a /32 as your initial allocation, you get a bigger one. And there've been many recent cases where ISPs, I mean, the ones I know are in Europe and Asia, have got a lot more than a single /32. And then the current policy, generally, summarizing, is that an ISP will allocate a /48 prefix to each end customer. So each end customer gets a /48. Now, if you think how big that is, that's actually a huge chunk of address space. Because within a /48, you've got 65,000 subnets. So it can number a fairly sizable customer site. So you don't have to do the sort of Spanish Inquisition into your customers' networks anymore. You don't have to say, okay, how many /32s, as in v4, /32s do you need? Right? How many hosts do you have? How many hosts will you have in 6 months' time or a year's time? Don't do that anymore. It's simply a case of, here, Mr. Customer, have a /48, go play. Okay, so it's intended to be greatly simplified like that. So I've written it out in the next few slides just to explain how big it is relative to v4. Now, 64 bits are reserved for the interface ID, so 64 bits are used for the local LAN. So I would say realistically, we've halved the size of the v6 address space already. So really, there are only 64 bits to play with in the networking field. Okay, for the local LAN, you've got 64 bits. And yes, that means you could potentially have 2 to the power 64 hosts on one network LAN. I have never seen a LAN that is approaching any size like that at all, but that's what the size is. I mean, the arrangement is to accommodate the MAC address. That was the whole idea. Okay? So you could do this automatic configuration based on your MAC address, and you'd no longer have to use DHCP and horrible things like that. We'll come to this in a bit later. 16 bits were reserved for the end site. So that's a possibility of 2 to the power 16 networks at each end site. So 2 to the power 16 subnets, 65,000 subnets. So me at my house, I could probably go to my ISP and say, hey, Mr. ISP, I want a /48 because I'm your customer. And they say, yep, here, have a /48. And I could number all 65,000 subnets I have at my house. I don't quite see this one particularly happening at the moment, but that's the scale of the current v6 setup. I mean, I've tried to put it into equivalent of v4. I mean, I don't know how realistic these numbers are, but I would say this is equivalent to giving your customer a /12 in IPv4. Okay, assuming 16 subnets, so 16 hosts per v4 subnet, which is, I suppose, sort of a reasonable average. Okay, you never imagine giving any of your customers anything this massive. 16 bits reserved for the service provider. So that means possibility of 2 to the power 16 end sites per service provider. So each service provider can have up to 65,000 customers. So you see now why some big ISPs have already got more than a /32, because they have gone to the registry and said, hey, we've got 1 million customers. So they've got a sufficient address space for those 1 million customers, and it's getting multiple /32s. If we try and convert it into v4 money, kind of, it's about the same as giving each service provider a /8 in IPv4, which, surprise, surprise, was sort of happening in the late 80s. So we're kind of back to that kind of generously handing out address space. 32 bits reserved for service providers, which gives us 4 billion possible service providers. I don't know if the planet is ever going to see that many ISPs, given we've got 6 billion of a population. But who knows in 50 years' time? Maybe when we have 100 billion population, it could be quite a reasonable number. Although an interesting aside I'll say here is, 4 billion discrete service providers. There are also 32-bit AS numbers have been extended to basically, well, the AS numbers are now 32 bits, so we have potentially 4 billion 32-bit AS numbers as well. So that's an interesting mapping, I think. So I'm kind of, my private thing is, well, how about just every ISP that gets a /32, just give them an AS number as well, because it's the same equivalent size. So, yeah, the comment from the audience is, do you think the BGP tables are big now? Absolutely, yeah. So here, what I've entitled the aggregation hope. So this was sort of the naive kind of, okay, if we give a /48 to a customer, then the ISP is going to aggregate into 32, and the v6 internet's only going to be full of 32s, and life is going to be wonderful. Well, any of you who have played with the v6 internet, I mean, I've been involved in it for, what, 12 years now? Well, you know full well that you don't see just /32s. And of course, there's the big question, right, with these 32s, how does multi-homing work? There's some folks who rigidly adhere to, okay, we should only see /32s, and I will filter on that boundary. How does multi-homing work? Okay? And one of the early promises of v6 was, yes, we're going to deliver you a multi-homing solution that's much better than the v4 one. And that's kind of just got forgotten about. So that's why I'm saying there, the current internet multi-homing solution breaks this rigid aggregation model. So what we're going to see realistically for any v6 internet, v6 routing table is exactly as we see in v4. People are going to take the allocation, slice and dice to get the traffic engineering and multi-homing that they need. And if you look in the v6 routing table today, yes, you see loads of /48s. You even see smaller stuff. Gert Doering does a nice sort of v6 routing table summary at the right meetings. It's sometimes been reported, whether it's here at the NANOG meeting or when NANOG and Aaron hold a joint meeting, but I remember it's been reported here as well, and you can see some of the interesting stuff that appears in there. Anyway, let's get back to the v6 things. So the lower 64 bits field of the unicast address can be assigned in many different ways. Remember I said it was made so big so that you can fit the MAC address in there? So this is this EUI64 thing that I've talked about on the slide, where you basically take your 48-bit MAC address, insert another 16 bits, and voila, you have your 64-bit, or final 64-bit of your v6 address. So that's how a lot of us have got our v6 address here in the conference network and during the v6 hour. The other way is have it auto-generated using a pseudo-random number. I mean, that was to try and address privacy concerns. I'll come to that one. I've got one slide that explains that in a second. Or assigned by DHCP. Yep, DHCP is also available there for v6, which in fact most organizations seem to want to use. Or you can manually configure the address, which is what most ISPs seem to want to use. So how does the EUI64 thing work? Well, you just simply take your MAC address. It's 6 fields there. You pull them apart, insert an FFFE in the middle, and then you have your 64-bit version. If you know that your MAC address is unique, then you set this bit in here as 1. If you don't know if your MAC address is unique, you leave it to 0. I mean, the chances of getting non-unique MAC addresses, I think, are, well, I always used to say it was reasonably rare until I saw, well, a few conferences ago, all the NIC cards on PCs all had the same MAC addresses, which I thought was quite interesting. Obviously, some cloning factory forgot to change the numbers, but they're all the same, so that made it. So I'm no longer claiming that MAC addresses are unique. So anyway, so the 64-bit address is now in there. So this is our final version. So these are the final 64 bits of your v6 address. Where do you get the rest of your address from? Well, you get the first 64 bits, you hear it from the router, which I'll show you a little bit later on. So the first 64 bits comes from the router. You work these out yourself on your own PC. Your PC does it itself. And that way you get your complete v6 address. RFC 3041, probably fair to say this was mostly motivated by Microsoft and regarding privacy concerns. You know, they were worried that their users, if they go browsing into places they probably shouldn't go browsing into or want to remain anonymous and so forth, people could work out who they are based on their v6 address, because you could figure out the MAC address and then track back to where they are. I mean, you can do this with v4 already, so I don't see what the big worry is. But anyway, so we've got this pseudo-random, I suppose, final 64 bits of the v6 address. As far as I know, this is only on Windows XP, and it's probably on Vista as well. I have not seen it on anything else at all. So this is this RFC 3041 address privacy thing. The v6 auto-configuration, so a couple of ways of doing it. There's a stateless auto-configuration where the host basically figures out its own address. Router solicitation is sent by any of these PCs, clients, whatever they are, saying, hey, any router out there, please tell me what the first 64 bits are. And then if there is a router out there, it responds saying, hey, my first 64 bits are these. So this is probably all fine and good in a well-controlled network, but when you have a network with lots of routers in it or spare Ethernet ports hanging on the wall and you don't know who could plug what in, it could be potentially dangerous. So that was a stateless auto-configuration, which is, say, useful for a network like here, probably useful for where you can control who can plug what into it, but probably not wonderfully useful for, say, a corporate network or a university network and so forth. So this is why we also have stateful stateful configuration, where you have DHCP v6, as we have DHCP v4, where a DHCP server, in the simple case, will basically hand out addresses to you. So there's no stateless auto-configuration available on the LAN at all. You have to get your address from a v6 DHCP server. There's also host renumbering as well. Basically, what you do is you configure the new address on the router, you put a lifetime onto the old address, and then the router goes out onto the LAN with the RA announcement saying, hey, new prefix is this is the lifetime of the old prefix, and in theory, the client will then migrate to the new address. So any new applications started on the client will use the new address, and when the applications using the old address are finished, the old address then hopefully will expire and disappear. There's also this router renumbering protocol, RFC 2894, and it's sort of interesting sitting here in the vendor side when people say, oh, have you got support for 2894? But when you look at it and you think about the possibilities, it's completely scary. It's a nice thing in theory, but if you imagine your network today, do you want something that just sort of comes in and magically renumbers everything in the backbone, just like that? I don't know many service providers who'd be very comfortable with that kind of thing. So you find that the router renumbering just hasn't been implemented. And it's just too much of a scary thing to do. Sure, it's easy changing IP addresses and interfaces, but what about your access list, your policies? You've got particular customer filters, particular backbone filters. What about interior routing, load balancing, and all this type of thing? All that will probably be dependent on your addressing. So having this just auto-magically renumbered isn't very appealing. So let's look at auto-configuration in a little bit more detail. So what happens is a client basically sends this router solicitation message. In other words, hey, any router out there, please tell me what's happening, more or less. The router responds with a router advertisement. So it just says, well, the prefix is this, and this is the default route. Notice, no DNS servers included in this. Okay, and this is one of the things that we saw with the NANOG v6 and the NANOG XPv6. On the handout that you got, it said the DNS server for NANOG v6 is this address, because the auto-configuration doesn't hand out a DNS resolver address. And without a DNS resolver, as far as you as an end user are concerned, there is no internet, even though you can probably still reach everywhere by address. So a client configures its v6 address by concatenating the prefix it gets from the router with the EUI64 address that it works out from the MAC address. So that's pretty straightforward. So if you have a v6 capable router on the network you plug into, you get connectivity, just like that. You don't need to involve anybody or anything else. Renumbering, so I've just described here. Router will send a router advertisement basically saying what the new prefix is, what the new default route is, and any remaining lifetime of the old address. And then the client will basically move over to the new address, configure the new address, and then expire the old address within the lifetime. There's a unique local addresses. Now, they've got an interesting history, and I think those of you who've heard me at different policy meetings ranting about some of this, I mean, there are a few others who rant about it as well. Unique local is intended for local communications within the local network only. And there was things like intra-site VPNs, basically anything that doesn't need to be routed over the internet. That was the big thing about unique local. Kind of a little bit like private address space, but no NAT for this. Okay, so a lot of people are using private address space for devices to communicate with each other within, say, an enterprise network. And those devices don't need any internet access at all. Right? So people do that. So we've got unique local. And unique local replaced something called site local. I mean, site local was the original one that was intended to do this. We've now got unique local, which to me as a sort of fairly innocent end user, it looks the same. And there's this whole big discussion about unique local and various policy things and people trying to do fancy stuff with it and so forth. Make unique local globally unique and things like that. Which is why I've said in the last bullet there, the future of unique local, as far as I can see, is unclear. I mean, certainly for using it in local networks, for devices that do not need any internet connectivity, it makes perfect sense. But then again, there's so much routable v6 address space. Why on earth do we even want to go down this path? Link local address, that's mandatory for v6. You find that any device that's going to use v6 will have a link local address. Link local gets set up, basically header with FE80. Remaining 54 bits here are generally just set to 0. And then you've got the interface ID built up the same way with the EUI64. So that's used for communication on links. Okay, so if your PC is connected to a router, you find the link local addresses, use that for that communication. If you have a serial connection joining two routers together, say over the WAN, you have a link local address used for communication across the serial. And then the globally unicast address is piggybacked on top of that. Multicast has more significant use in v6 than it has in v4. We have broadcasts in v4. Those of you who have been around long enough will remember the broadcast storms that we saw on, well, different networks, especially with vendor defaults being inappropriate, like broadcast being enabled in interfaces. Well, that's all been fixed, but at the same time, v6 has basically thrown away the whole broadcast concept. And so there's multicast is used instead, which hopefully is more efficient than the sort of splattercast that you got with broadcast. The v6 multicast address, FF00/8, I'm not going to go through this in detail because I really know nothing about a v6 multicast at all. The first 8 bits are all set to 1. The next 4 bits is the lifetime of the address, so it can be either temporary or permanent. The next 4 bits are the scope, and then the final 112 bits are the group ID. And the scope of the multicast address, well, you've got those options, whether it's node, link, site, organizational, or global. Some examples of where multicast addressing is used. Well, RIP-NG uses multicast. So RIP-NG is the v6 version of RIP. I'll mention these again a bit later on. It uses FF02:9. So that's a specific address that RIP-NG uses. So if you decide to go filtering multicast on your v6 network and you're using RIP-NG, make sure you allow FF02:9 through. Same goes for OSPF v3, and if you're using Cisco's EIGRP, the same goes for EIGRP. I mean, I've seen many cases, even in v4 land, where people decide, ooh, I've got these v4 multicast packets on my network. They shouldn't be happening. Filter, and the OSPF falls over. Okay, so be aware that v6, if you're going to use the v6 IGPs, allow these multicast addresses through any filters. v6 Anycast is interesting. RFC 4291 describes the v6 Anycast in more detail. I haven't actually seen anybody who actually uses it the way that the RFC intends. In fact, most ISPs or most operators are using Anycast in the way that v4 Anycast is used. Okay, they're not actually saying this is a v6 Anycast address. They're just simply saying, okay, we've got this address popping up in lots of places, and they're treating it the same way as v4 Anycast. And just in case you don't know how Anycast works on the internet, well, what it is, we've got a global address, and a server is recognized by a particular global address. It could be, say, a root name server. It's recognized by that one address, but that one address pops up in 20, 30, 40 different places around the world. And it's basically up to BGP to figure out the closest address for the end user. And that's how the v6 Anycast is being used as far as I can see. So if you look at, say, the root name servers, I mentioned those, some of those operators now have a v6 address for the root as well, and they Anycast those v6 addresses in the same way that they've Anycasted the v4 addresses. Anyway, typical uses of v4 Anycast today, and I should probably fix this, are the root DNS, CCTLD, GTLD name servers. Quite a few ISPs use them for SMTP relays within their own backbones as well. So that's typical use of Anycast today, whether it's v4 or v6. MTU, well, the minimum link MTU for v6 is 1280 octets. That's a wee bit bigger than the 68 octets we had for v4. But if you think back to when v4 was being used, I mean, we all had, what, 75 baud modems, 1200 baud modems, that kind of thing. We're trying to run IP over that. So 68-byte MTU kind of made sense. These days, we're all dealing with fiber and wireless and big, fast media. So 1200-byte octet seems to make an awful lot more sense. I mean, Tom Skoll earlier was talking about making the MTU on the internet even bigger than it currently is. So there could be some argument that even the v6 one of 1280 octets is on the small side. If links can't handle MTUs of this size, then you have to do specific fragmentation and reassembly. There's no kind of just the disassembly, reassembly that you got in v4. v6 assumes you have to be able to push 1280 byte MTUs through the network. A minimum implementation of v6 can miss out path MTU discovery if it wants, as long as it can transmit packets greater than or equal to 1280 octets. You can also get this hop-by-hop thing that supports jumbograms with up to 2 to the power 32 octets of payload. Again, on the real internet, I've never seen this. I realize this is of great interest to the academic and research community, where this seems to be more of an issue for them. Neighbor discovery, well, that's built on top of ICMP v6. So it's a little bit like ICMP or the ICMP, IGMP that we had in v4. Basically lets you find out the neighbors that exist on a particular v6 network. So there are various ICMP v6 packet types. We've seen the router solicitation, router advertisements before. There's neighbor solicitation, neighbor advertisements, redirects, and so forth. So that's kind of a little bit like ICMP, but a bit more enhanced. So I would say, as far as we're concerned, as the end user, nothing is different. v6 and the DNS, well, not a great deal of amazement here. For v4, we basically had A records. So you populate your DNS, you had www.abc.test, A record, something. Well, for v6, well, because a v6 address is 4 times longer than a v4 address, they just made it quad A records, rather than B records or something else. It was simply quad A, and that's what it's called. So you see a quad A record, you put the name in, quad A, and then the v6 address goes in there. The reverse DNS, in my humble opinion, is plain scary. I mean, for v4, it was bad enough trying to encourage operators to populate the reverse DNS. I mean, in this part of the world, say Europe, North America, it's no problem. Trying to encourage operators in Asia and so forth to populate the reverse DNS, because they seem to think that no reverse DNS means that your network's secure, it's hard work, because, it's really complicated to do the reverse DNS. Because they've got to deal with this whole in-address ARPA and pointer things, and how do you do it for /27 and all this kind of stuff. Well, if you look at it for v6, I don't think this is doing anything to try and encourage people to use the reverse DNS either. I mean, yes, there's a tool, which a name I forgot to put onto the slide here, and a name who I've forgotten standing up here. There's a tool that will build all these reverse files for you and forward files to make it easier. But when you actually look at the zone file and to try and handle the IP6 to ARPA reverse, it's intimidating, let us say. But that's what the reverse DNS looks like. There's basically a dot between every single number that appears in the v6 address. And even the zeros that get dropped when you write the address normally have to be included in the reverse. Right? You can't miss the zeros out, otherwise the reverse resolution doesn't work. So the v6 DNS, you're going to have to start looking at tools. Hand cranking this is not really going to be an option going forwards. As for the technology scope, I mean, one of the things I always end up doing in much of my travels is participating in v6 forums and v6 marketing meetings and so forth, where all the v6 marketing people are standing up and saying, oh yeah, v6 does this, it makes your laptop battery last longer, and it guarantees quality of service, and guarantees round trip times, and security is guaranteed, and all this other kind of stuff. And it quite literally is stuff, because what's happened is v4 has been developed continuously at the same time. Pretty much anything and everything you see with v6 offers today, v4 can do too. So the differences, addressing range, v6 is 128-bit rather than 32-bit. Okay? Look at auto configuration. Sure, DHCP for v4, DHCP for v6. Yes, we've got serverless and reconfiguration as well. IPsec, v4, v6. Okay, there's no difference. I mean, if you try and find an implementation of v6 today that's using IPsec by default, it doesn't exist. Okay? Mobile IP, well, you get direct routing with v6. But that's still doing a lot of work trying to figure out how to make this work properly and reliably and safely. Diff-serve, quality of service is one of the big things for v6, but it's no difference from what you can do in v4. Right? So there's no such thing as guaranteed round trip times. I mean, if v6 would guarantee round trip time, say 50 milliseconds between here and Australia, it'd be wonderful. I mean, we'd probably break the laws of physics completely doing that. Okay, Einstein would be wrong. And that's what seems to be some of the marketing people are saying. They should stop and think before they start making these claims that simply aren't realistic. And for IP multicast, there isn't really a great deal for me standing here as a kind of end user viewer. Yes, some of the things are slightly different, but in principle, it works the same way. What does v6 do for security? Nothing. Okay? IPsec runs in both. If you do security in v4, you will have to do the same security in v6. I mean, the only thing is we've got less experience of running v6 in a real world, in a real network, so there are probably holes that we haven't even thought about. I mean, I should mention what was the IPv6 source routing thing from last year. I mean, we discovered that in v4 years ago, but it was only just discovered for v6 last year. Things like that, you know, we haven't got the sufficient experience really to look into it. What about quality of service? Okay, there's nothing new in v6, so we don't need to worry on that side. As for the standards, I mean, I've put up a load of RFCs here that, you know, there's a lot of stuff here. A lot of people support a lot of what's on here as well. IPv6 will run over most types of infrastructure, so it's PPP, FDDI, NBMA, Frame Relay. IEEE 1394 if you really want to do that. Anybody remember ArcNet? I mean, I'm sure somebody's still running ArcNet somewhere. You can run v6 on ArcNet because, hey, there's an RFC that describes it, and so on. So you can run v6 on pretty much anything. So there's no big issue there. So where am I with time? Not a lot left. Let's have a look at addressing. So where do you get v6 address space from? I'm probably going to upset registries and registry people with some of the things I'm going to say, but trying to help people get through what could be a morass of, I suppose, policy documents and so forth about how to get addresses. It's not as hard as can be made out, let us say. First thing, you can become a member of your own registry, regional internet registry, get your own allocation. So for most of you, this will be Aaron. I know some of you from Asia Pacs, that will be APNIC. All you need is a plan for a year ahead. We had this amazing discussion in the APNIC policy list. A plan is not a commitment to do something, that if you don't do it, the registry will come and smack you. Right? A plan is simply that. Okay? I have a plan to do whatever. I have a plan to go to the moon tomorrow. That's a plan. Okay? I may not be able to do it. I know I can't do it, but it's a plan. So that's all they're looking for, a plan for what you're going to do in the next year. So if you've got some customers and you say, yep, I'm planning to give my customers v6 address over the next 2 years, actually, in some cases, that's all you need. But look at the registry website. Each of the registry has their own specific policies. You can take part of your upstream's /32 address blocks. You can get a /48 from them. And if you go into multi-home between different upstreams, you get a bit of a challenge. But if you're simply connected to your own upstream, get a /48 from them, and you don't have to worry about dealing with the registries. Use 6-4. Okay, I'm going to talk about 6-4 in a little bit. 6-4 is not a way of getting v6 networks to talk to v4. But 6-4 is a way of you getting onto the v6 internet without having to bother your upstream ISP or go to the registry. And the final point is there is plenty of v6 address space. All the registries, as they do with v4, they just want some documentation. So they can point to whoever wants to count the beans where the beans have gone. So from the registry, you'll get a /32 or more if you've got more than 65,000 customers. From your upstream ISP, you'll get a /48. If you've got more than 65,000 subnets, you get more than a /48. Or you can use this 6-4 thing, where you take your single IPv4 /32 address and give yourself a whole /48 out of that. Basically 2002 : your v4 address /48 becomes your v6 address block. Now it gives you 65,000 subnets, and it's fully routable across the whole internet. I've been using 6-4 at home for the last 7 years at my home network. So I'm all reachable through 6-4, and all my v6 networking just works like that. So I haven't gone to APNIC. I haven't gone to my upstream ISP. The last time I asked them, they said, what's IPv6? Do we need it? So they're that far away from things. So I've been using it quite happily. I'll come to 6-4 in a bit. So for the ISP infrastructure, so ISP should get a /32 from the registry. How we do the numbering, I think, is quite important. This comes more from experience of trying to do workshops and trying to help ISPs do initial deployment plans. Try and address the block for the router loopback interfaces. If you do that, number them all out of a single /64. Right? A loopback only needs to be a /128, and that's all fine. So you've got 2 to the power 64 possible routers in your backbone. That's probably enough for most people for a while. Set aside one address block for infrastructure. Okay, a /48 gives you 65,000 subnets. I mean, if your infrastructure needs more than 65,000 subnets, then set aside 2 or 3 or more. Okay, so some people just do a whole /48 for the entire backbone. Some do a /48 per POP or per region. It's really up to you. It depends on the size of the network. I mean, I've seen people go to registries and say, "Oh, how should I do the /48? Should it be this? Should it be that?" Registry doesn't care. They're the ones, well, you're the ones who know how to run your own network. So if you see a network scaling to an extent that you outgrow a single /48 for the whole backbone, then do it per point of presence basis. And that is probably a more sensible thing to do. What about LANs? Easy, /64 per LAN. So when you were growing up and you learned about putting Class Cs onto Ethernet LANs, yep, you need to relearn all those bad habits again. Right? /64 for LAN, nothing else. If you do anything else, auto-configuration doesn't work. What about point-to-point links? Well, the expectation for those is /64 should be used as well. But people have used /126s, but mobile IPv6 home agent then won't work. Okay? So /126s seem to work for most cases. If you don't care about mobile IP, then fine. Some people have used /112s. Then mobile IPv6 home agent discovery does work. Okay, so some operators are converging onto /112s. Others are still using /64s. Others are using /126s. Okay, RFC 3627 has got some discussion about each of these. But is there a recommendation from the industry? Is there an industry best practice? I would probably argue that there isn't really one. And you really need to try and pay attention to what folks in the industry are doing. I mean, what I do in my own workshops, I just use /64 for all the point-to-point links, which is scarily wasteful when you look at the amount of address space that's involved with a /64. But then, understand the issues with /126s, /112s. Some people are looking at /96s. So whatever you try and feel comfortable with, I think take a look at what the industry is doing and make your own decision based on that. Customers get one /48. Okay, they get one /48. You don't need to sort of do the Spanish Inquisition, as I said earlier, just a single /48, and then hopefully it's fit and forget. I mean, if they've got more than 65,000 subnets, then give them a second one, a third one. But again, and I encourage you to take part in the registry policy process, there's big discussion going on in all the registry regions about, oh, well, /48 is a bit too much. It's stupid me getting a /48 from my mobile phone. Or my example earlier, stupid for me to get a /48 for my house. I don't have 65,000 subnets there. So there's this discussion about, well, maybe small customers should get a /56. And maybe single LAN end site should only get a /64. Which is, it's a good discussion, but then you've got to think as an operator what you're going to see in your BGP table. If you go start giving /64s out to your customers, you could see the internet routing table have lots of /64s in them. Anybody seen a router that can carry 2 to the power 64 prefixes in it? Big number. I mean, I'm not trying to be scaring or anything like that, but it's a number to think about. Other recommendations, try not to reserve address allocations on a per POP or anything basis, because you're using IBGP, that can carry big prefixes and so forth, so it's not really necessary. Just emphasizing my other hobby horse, aggregation within IBGP you don't need to do. Aggregation for eBGP is very, very necessary. Leaking your IBGP out into the internet is generally not a wonderful idea. So I've tried to sort of explain how some of this might work in a sort of funny diagram. I've used the documentation address, so this is not routed on the internet. So you set aside a 64 for your loopbacks, then you've got your /48 here for your infrastructure, and then you've got the remaining 65,534 35 subnets for your customer assignments. And then when you run out of address space, you go back to the registry. The way they do the sparse allocation for all the membership, in theory, or hopefully, you should get the neighboring or adjacent /32. And if you do, you can aggregate it into a /31. And then you just do your numbering plan with that. So as I say, the registries will usually well, they'll try and allocate the next block. I mean, the way they do the allocation at the moment is they get the /12 from IANA, and they do a kind of binary search type allocation out of it. So it's a sparse allocation, and they fill in the gaps as more members require v6 address space. So if you go back asking for more, it's highly likely you'll get an adjacent /32 or whatever. Let's look at the routing protocols. Should just have time. Static routing in v6, hey, it's unchanged from v4. Okay, all that has changed are the numbers. So default route is now : /0. It's a lot less to type than 0.0.0.0. Okay, so it's a lot less to type. So that's a saving in v6. In fact, if you look at most router platforms, the CLI is different. I mean, it's unchanged. All you have to do is just look for v6 rather than v4. So for example, in iOS, rather than IP route something, we do IPv6 route something. And you see all the same parameters. So the network you're trying to reach, the next hop address, and any protocol administrative distance after that. So it's very, very simple. What about dynamic routing protocols? Well, they're unchanged too. Okay, we've got internal routing protocols, the IGPs. We've got exterior routing protocols, the EGPs. We still use longest prefix match routing algorithm. That hasn't changed. So if you understand how v4 routing protocols work, all you have to do to understand how v6 routing protocols work, quite literally, is to learn the CLI. Okay? So learn how hexadecimal addressing works. I mean, people who come to the v6 routing workshops end up being really disappointed in some way because they expected they're going to learn something completely new. They didn't expect that they're going to come to hear me give them a lesson in hexadecimal addressing, which is basically all it is. So for interior routing protocols, we've got RIP-NG, RIP next generation. We've got Cisco's EIGRP. We've got OSPF v3. And we've got ISIS v6. BGP now has been extended to be multi-protocol, so it'll handle the v6 address family as well as the familiar v4. This is probably platform dependent. It depends on your router vendor and what they do by defaults. Dynamic routing protocols generally require a router ID, which is a 32-bit integer. If you're doing v6 in the complete absence of v4, you have to configure a router ID by hand. Because a lot of v4 routers, setting up v4 routing protocols, they'll conjure up a unique number from the router configuration, normally from the loopback interface address or maybe from a real live LAN address or something. But anyway, most ISPs are going to deploy what's called dual stack. You're going to run v4 and v6 at the same time. So if you're running v4, getting a router ID for v6 is no problem. But I don't know, a few years ago, I had some early adopters who were determined to run their own v6 networks with no v4 at all, and they got stuck with this. They forgot to put in the router ID configuration, so the router just said, well, I'd love to run the routing protocol, but I've no router ID, so not playing. So RIP-NG, ISP industry, just don't go here. The early 6-bone used RIP-NG, and that was major encouragement to develop BGP supporting IPv6, let us say. Okay, just don't go here, don't touch. This is for people who don't want to learn routing. OSPF v3, the two IGPs that are widely used in the industry, OSPF or ISIS. If you're using OSPF v2 now, OSPF v3 is probably a sensible strategy for you. If you're using ISIS just now, then adding in the v6 address family support for ISIS is probably most sensible for you. The thing with OSPF v3 is it's based on OSPF v2, but actually has no interaction with it at all. So-called ships in the night. Okay, so OSPF v2 plays with its topology, OSPF v3 plays with its own topology. There's no interaction between the two whatsoever. So if you want to deploy v6 over a little piece of your network, you can use OSPF v3 for that, have all the proper reachability, and it doesn't matter what the OSPF v2 looking network looks like. Okay, so that's pretty nice. Differences, well, OSPF v3 runs over a link rather than a subnet, although I've seen most implementations these days, OSPF v2 can also run over a link as well. Topology is not v6 specific. It got standard authentication mechanisms, so, well, certainly looking at iOS, it uses IPsec now for authentication rather than its own built-in thing. Link local addresses are used rather than the global unicast addresses, and the 2 new LSA types. I'm not going to go into the detail. The v6 routing tutorial, if you look at the last NANOG, was it last NANOG? I think it was. The Albuquerque meeting, I did the v6 routing tutorial there, so have a look for the greater detail about OSPF and ISIs in that. For ISIs, well, a bit of history of it. It started off being a routing protocol for CLNS traffic. So TLV was added basically to enhance the protocol, so then we could add IP support in there for v4, RFC 1195 to find that. And then v6 address family support was added. It's been lingering there as an internet draft for, I don't know, 4 years now. I don't know why it's got stuck or so forth. But anyway, most of the major vendors I know have implemented ISIs v6 based on that particular draft. Multi-topology has also been added for ISIs. And the reason for this is the standard ISIs, the v4 and v6 topologies have to be the same. And that was a problem for some of the early adopters of v6 because they wanted to set up ISIs, well, v6 in a little corner of the network. They didn't want to deploy it over the entire backbone. But the way the ISIs had the address family support added was it had to be exactly the same topology. So this is where the multi-topology support came in, which lets you have different v4 and v6 topologies, a bit like you can have with OSPF v3. And again, you just have to look at what your vendor default is. I mean, Cisco IIS default is non-multi-topology, so you've got to switch it on, whereas Juniper default is multi-topology is on, and you've got to go and switch it off if you don't want that. So the various bits have been added for ISIs v6, so the 2 new TLVs, the 4 new TLVs for the multi-topology, and so forth. I won't spend time on this. As for BGP, many of you have probably played with VPNs and BGP. So v6 is simply another address family. So we've got the v4 address family, we've got v4 unicast, v4 multicast, we've got v6 address family, and the 2 sub-address families, unicast and multicast as well. So that was a very, very simple addition. So for your router CLI, it's probably you've got CLI that says address family v4, address family v6, and you just simply set it up in parallel to the existing v4. So again, it's a case of simply learning how to handle the v6 addresses, because it's all the same as v4. So just the final piece, the integration and transition piece, which I'm probably not going to have time to go all the way through, but I'll try and skate through as much of it as I can. Coexistent transition. So many people have talked about migration to v6, which basically means, well, seems to me to mean is like switching off v4 and using just v6. I don't think that's going to happen in, well, my working lifetime anyway. We're going to be running with something that's called dual stack for quite a long time. Dual stack basically means we've got v4 and v6 sitting on the same device and on the same network. So there are a lot of networks around the world that are already dual stack. They've got the existing v4 internet infrastructure, and they basically dual stack all the routers to run v6 as well. You're also going to find that there'll be tunneling techniques, which tunnels are quite useful for getting around bits of the network that are simply too old to be upgraded to handle v6. You may have some really old devices or so forth that can't do v6, so use a tunnel to get past those. And there'll be various translation techniques as well to allow v6-only devices to communicate with v4-only devices. Again, you saw in the v6 how we're trying to get NAT-PT sort of working, and it sort of worked for most folks. So that would be an example of a translation technique. So pretty picture with dual stack. This is pretty much what's going to happen. We'll use v6 if possible. If there's no v6 destination for the client, then we try and use the v4 destination. So how it all is actually going to work, dual stack with DNS, well, the way it will function is basically you have the system here trying to reach a destination. So what it does, say it's www.a.com, so they'll go and ask the DNS server, hey, give me a v6 address for this particular website. That's the first thing that happens. So if your device has got a v6 address, as well as a v4 address, the first thing it should do is ask for a v6 address for the remote site. If the DNS server says no, then it says, oh, okay, give me a v4 address. And then if it gets a v4 address, you get connected. If the DNS server responds with a v6 address, then you get connected through to the v6 site. Okay? So it's really how it works all based around the DNS. And this was, again, the thing that we had set up with the NetPT at the v6 hour. We had a DNS server, which basically would give you a real v6 address if the site had a v6 address. Otherwise, it gave you a fake v6 address, which then would let you tunnel through the NetPT to get to the v4 site. Sample use stack configuration. I mean, I've got an iOS snippet. It's probably a waste of time showing this, but it's basically you've got your v4 address in here, and then the line underneath, you've got your v6 address. You don't need to do anything more. There's no other magic needed to configure anything, certainly on the routers. Using tunnels, there's a whole variety of things that people get excited about, all the different techniques to establish tunnels. Quite frankly, only a few of them are interesting. Manual tunnel, I mean, we've got a manual tunnel for the v6 connection from the conference network back to Merit. So that's a manually configured tunnel over the existing infrastructure. So the manual tunnel could be an IPv6 tunnel running over IP, or it could be a GRE tunnel. You need to use a GRE tunnel, for example, if you want to run ISIS over the link. People have heard of tunnel brokers. You can go to a website and you can click on it and they give you an IPv6 address and you can then set up a tunnel to this tunnel broker site. So some people use that. Or you can use automatic tunnels. I mean, the 6-to-4, ISOTAP, and Teredo. ISOTAP and Teredo are only really interesting for enterprises, in my humble opinion. I don't see them having much use for service provider networks at all. However, 6-to-4 is interesting for a service provider network, and I would say it's pretty interesting for the enterprise also. Let's have a quick look at them. So the manual tunnel, so we've got the v4 internet here, and so we simply build a v6 tunnel over the v4 internet, or under the v4 internet, whatever terminology you want to use. So that's a simple example of how you configure that. The 6-to-4 tunnel is a little bit more interesting, because you can basically set up a tunnel without really caring what the other end is doing. It's got special address space. Basically, this 2002 signifies a 6-to-4 address range. So the 6-to-4 address range is the /16, 2002. You take one routable IPv4 address, a single /32, and drop it into the next 32 bits. And that makes up your 48 bits for your v6 address space. Right, so you've got your v6 network here. It's made up its /48. So how do you get to the remote network? Well, the remote network you also know is using 2002 : something or other. So what happens is this 6-to-4 gateway router will realize that the destination is a 6-to-4 address. It knows that the next 32 bits are the v4 address, and it will encapsulate the v6 packet with a v4 header, send it to the v4 destination. This router 2 over here sees that it's a v4 encapsulated v6 packet, strips off the v4 encapsulation. There you have the v6 address, and it carries on inside the v6 network. So that's pretty neat. So it means that sites that are using just 6-to-4 can use just 6-to-4 to communicate with each other without the core internet actually have any idea that this is going on at all. 6-to-4 relay is more interesting because it means that a remote v6 network can basically take a single v4 address and get full v6 connectivity without anybody else, anywhere else having to do anything about it, because they rely on this 6-to-4 relay. A 6-to-4 relay is basically a gateway between the v6 internet and the main v4 network. Okay, so what the relay does, the relay will basically announce to the v6 internet that it's a relay. So it announces the 2002:/16 address block. So when packets come in within that address space, it knows to unencapsulate them, if appropriate, and pop them onto the v4 network. Or the other way around, 192.88.99/24 is announced to the world, again, as basically as a means of converting back into the v6 space from the v4 internet. So if you announce 192.88.99/24 to the v4 internet, you're advertising a 6-to-4 relay capability. And so basically, any encapsulated packet will head towards this address here and get popped back into the v6 internet. So this v4 address is an Anycast address. I mean, the last time I looked, I think it's 6xs.net list how many 6-to-4 relays they think there are. There are about half a dozen, or just over half a dozen of these in various spots around the internet. Quite a few service providers advertise these, or set up these devices. And I try and encourage ISPs who've got like a spare router lying in a corner just to set up something like this. If you announce the 2002/16 and the 192.88.99.1/24 network out to the internet, then you provide this 6-to-4 relay service, which is actually really, really handy. And all you need to do is just point a static default route on the relay router to, sorry, this is not the relay router, but towards the relay router, and you end up in any of the 6-to-4 relay routers around the world. I mean, I've used that quite a lot. I mean, that's how I get my V6 access at home. And it's quite surprising that RTTs almost match the V4 RTTs. We don't really get any of the wacky or weird routing that you'd normally associate with the early V6 internet. Okay, so 6-to-4 I think is pretty neat. So that's basically summarizing what I said about all that. So the next piece I want to look at just for time is the tunnel broker. You go to the website, HTTP, v4, you pick up your tunnel address, and then you basically build the tunnel to the v4 device that they've specified, and that gives you access to the v6 internet. So there are several organizations around the world who offer this tunnel broker service, and it's a way of giving end users access to the v6 network. NATPT for v6, well, old RFCs, 2766 and 3596. Well, 2766 describes NATPT. 3596 has just added a bit more detail to it. Basically, this is the one that does translation. So it lets v6-only sites see the v4-only internet. And it says there in the final bullet, easy-to-use transition and coexistence solution. I'm not sure if I'd even agree with my own slide after my effort in trying to get the iOS 1 working earlier today, but it should be easy to use and so forth. Basically, what you do is you set aside a 96-bit prefix to basically be your sort of dummy v6 address that's going to be used in your v6 world. So that dummy address is basically then used to map onto v4 destinations. So it's a bit like v4 NAT in itself. You've got a kind of pool of addresses or a range of addresses that can be used for the translation. So the way NATPT works is a little bit like this. So we've got our v6 host out here with this nice big address sitting there. We've got the v4 host sitting over here. I mean, I've used private addresses as examples. I mean, in real life, you'd use public, of course. So basically, you've got this packet coming here. Source is, well, that address. The destination is whatever you've chosen to be this dummy prefix. I mean, the way we did it in the v6R was basically the name server gave back this dummy address. You saw the address was something or other, and then it had this double AA sitting in the middle. Okay? The NATPT device recognized this as this special translation prefix, and then what it does, it translated it. It translated into whatever the v4 address is really meant to be. Okay, and then the v4 host responds, so its source is coming from 172.16.1.1, destination 172.17.1.1. So you've got a v4 address pool that basically maps back into the v6, and then the NATPT device basically maps it back into the v6 world. So this is how it all should work in theory, and NATPT working well is pretty much mostly transparent to the end user. And I think, at least, I was amazed how many people put up their hands at the end of the v6 hour saying they actually could do stuff during the v6 hours. I was expecting maybe 2 or 3 people to say, yeah, it worked, but it was probably about, I don't know, half the room, which was extraordinary. And this is how the DNS application layer gateway works. So basically, your host will send out a request for, host whatever the domain is. And the NATPT device basically will intercept this and say, no, it's not a quad A, it's actually just an A request for this particular destination. Response comes back, the address is this. The NATPT basically gets involved and says, this is an A record. We can't do A records in v6 network. Let's convert it into the quad A and give us the translational v6 address we're using. So it uses this translation address that I've picked 2010:45. So as far as the v6 host is concerned, that remote site, host.netpt.com, is actually sitting on 2010:45, whereas it's actually sitting in the v4 world. Okay, and then you do the same request for the pointers. So he asks for the reverse IP6.ARPA address, and the NatPT translates it into an in-address ARPA. The response comes back, and of course the pointer record just gets transited straight through. So that's certainly how the DNS application layer gateway worked, and it's how the TOTD application layer gateway was working during the, well, it's still working now, but during the v6 hour for those of you who are using the NatPT then. So summary of all this, you've got an application layer gateway per application. Certainly DNS is the way that things are done. Things like FTP and so forth aren't really handled yet, but it's work in progress. For some reason, NatPT was deprecated within the IETF, although that seems to be changing now. So NatPT is going to be pretty important going forward, I think, as more people want to develop or deploy v6 in the network. And we're going to see more of this coming from your vendors and different sources. Problems with NatPT, of course, is there's no end-to-end security. But then, hey, we don't really have end-to-end security for a lot of what we do in v4 anyway. No DNSSEC. Well, I'm sure somebody can try and figure out how to do DNSSEC through an application layer gateway, but so far there isn't any. And of course, there's no IPsec because you're in different address realms. But it is a pretty easy v6, v4 coexistence mechanism. That's pretty much all I plan to do. What I've done in the last few slides was just put in, it's just for information, but how to configure v6 for various servers. So if you haven't figured this out, I can't find the documentation. It's like how to set up the Apache server to handle v6, how to set up bind9 to do v6, how to do sendmail for, get your sendmail thing to support v6. Not that many people use sendmail anymore, but this is just how to do it. Various Unix applications, and so forth. We've collected a lot of this on the Cluster 5 wiki and so forth, and the URL I mentioned earlier about what different applications need to have done to them to make v6 support work. We look at the different operating systems. Mac users always say, oh, we've always had v6 and it all just works, but certainly Chris Morrow and I have found out in the last day or so that it's not quite as straightforward as that. Like not being able to paste capital letters of a v6 address is just positively weird. And the various Linuxes have had v6 running there for quite a long time. XP, simple enough to install. I've played with the Windows 2000 version, the early development stack, and that's kind of just worked too. Vista has it enabled by default. Not going to go into much of that. And most applications will probably use v6 transport if there's a v6 address offered. And at really high speed, which I apologize for, that is all of the introduction to v6 tutorial. As I said at the start, if you want to see some of the detail of the router configurations, certainly on Cisco iOS and iOS XR and on Junos, have a look at the tutorial I did the last NANOG, which goes through in some detail about how to configure all of that. But I hope this has been a useful introduction and given you a little bit of a background as to what we did for the network here today, well, especially in the v6 hour today, so you see how some of the bits actually ended up working. Main thing I want to summarize with is that v6 should not be a big, scary thing for anybody because it more or less works the same way as v4 does. You really just have to get a handle on the big addressing, the hexadecimal addressing, the double colons, the different ways of representing defaults and so forth. And otherwise, take confidence in that and try and move forwards. And when you go back from this, I think what to do, issue the challenge to your CTO and so forth. What's your business plan after August 2010? What you're going to do when Aaron is no longer able to give you v4 address space? Do you want to go into the market, or do you want to do something different? And that's all I have to say. Thank you very much for listening. If there are any questions? So if there are any questions, please ask. I won't be around much longer because I've got to rush off to Apricot and Taipei, which is clashing with NANOG, unfortunately, but you can try and grab me this evening and first thing tomorrow morning before I head off.
Quick question, Philip. Ann Johnson from CPacket. You said early on you were going to say a little bit about the flow record field, and then you skipped it.
I did, didn't I?
Is it really irrelevant? Because my curiosity is, does it have anything to do with net flow or S flow, or is it a completely different concept?
It has nothing to do with net flow or S flow or anything like that. Nope. And I haven't really seen any serious doing anything with the flow record yet at all. I mean, there's been some talk that I've looked at. I could be completely wrong here. I mean, people who are probably involved playing with that are probably say, oh, no, there's this happening. But if I look on routers and what service providers are talking about, I see no implementation. But no, it's nothing to do with NetFlow or SFlow or IPv6 or anything else. Okay, well, if there are no questions, I mean, I welcome feedback, how to make this better, things to add, things to delete, things that were wrong. Please let me know. Otherwise, thank you very much.